Now we're going to talk about antibody targets and function and some of the defense mechanisms that are accomplished by antibodies, which are listed here. The acronym for these is PLAN, where the P stands for precipitation, the L stands for lysis by complement, the A agglutination, and N neutralization. So let's talk about these in more detail. So one of the simplest and most effective ways is going to be neutralization, where the antibodies are going to go and block harmful parts of the viruses or bacterial toxins and prevent them from attaching to and damaging our own body cells. And then these antigen antibody complexes are then easily going to be removed by phagocytosis. In agglutination, each antibody can bind to two antigens at once, if you remember that Y-shaped structure. And this is going to cause the antigens to clump together into a larger lattice-like structure. And this clumping makes it easier for the immune system to clear them, as we've seen previously with the agglutination or clumping of mismatched blood cells. We also have precipitation. And this occurs when antibodies bind to really small dissolved antigens, and they're going to form this solid complex that fall out of solution, making it a lot easier for phagocytes to go in and engulf it. And then lastly, we have complement fixation and activation, and this is a major defense system against cellular antigens like bacteria. So when antibodies bind closely together on a cell surface, they're going to activate the complement system, which is going to lead to cell lysis and enhance inflammation and phagocytosis. So all of these combined actions make antibodies really powerful tools in helping fight infections. So here's just an illustration of the things that we talked about. Once we form an antigen-antibody complex, we have three mechanisms by which we can inactivate the antigen. One is the neutralization, then we have agglutination or clumping, and then precipitation. We can also trigger with this complex complement activation, and what they're showing you here is C3, which we've already talked about, being lysed into C3b, which is going to basically polymerize and form the MAC complex that we talked about, which is a pore in the plasma membrane of the microbe, essentially causing lysis. The other component from the lysis would be C3a, which can go on to help enhance inflammation. So just a little bit on monoclonal antibodies. So monoclonal antibodies are identical to antibodies that are produced by a single clone of cells, and they're really designed to bind to one specific antigen. And they're made using what we call hybridomas, which are created by fusing a specific antibody-producing B cell with a cancerous myeloma cell. And this fusion creates a hybrid cell line that can divide indefinitely and therefore is going to produce huge quantities of whatever the antibody that we want to produce is. So monoclonal antibodies are widely used as clinical tools, so things like cancer therapy, even COVID-19 treatment, and even some autoimmune disease management, as well as research tools like for detecting specific proteins in tissues or cells. Their high specificity really makes them valuable for both diagnosis and targeted treatment. So this is something fairly new, and there's going to be a lot more research using these as well. And this is just a nice little summary slide talking about all the things that we've discussed regarding